Have you ever looked at a rooftop covered in shiny blue panels and wondered how those simple sheets of glass can power an entire home? It almost seems like magic. That sunlight, something we experience every day without giving it much thought, can be transformed into electricity capable of charging phones, running refrigerators, lighting cities, and even powering spacecraft millions of kilometers away from Earth. Yet behind this remarkable technology lies a fascinating combination of physics, chemistry, and engineering that has been refined over decades. Solar panels have become one of the fastest-growing sources of renewable energy in the world, helping reduce dependence on fossil fuels while providing clean electricity from one of nature's most abundant resources. But how exactly do they work? Let's explore the incredible journey of sunlight becoming usable electrical power. Everything begins with the sun, a giant nuclear fusion reactor located about 150 million kilometers away from Earth. Every second, the sun releases an enormous amount of energy in the form of light and heat. Tiny packets of light energy, known as photons, travel through space at the speed of light and reach Earth's surface in just over 8 minutes. These photons carry energy, and solar panels are specially designed to capture as much of this energy as possible instead of allowing it to bounce away. The heart of every solar panel is a material called silicon. Silicon is one of the most common elements on Earth and is found in ordinary sand. However, the silicon used in solar panels is purified to an extremely high level so it can efficiently interact with light. A single solar panel contains many smaller units called photovoltaic cells. The word photovoltaic comes from two ideas: photo, meaning light, and voltaic, referring to electricity. Together, photovoltaic cells convert light directly into electrical energy, without moving parts, fuel, or to understand how this conversion happens, imagine silicon atoms arranged in a neat crystal structure. Normally, electrons inside these atoms are tightly bound and cannot move freely. However, when a photon from sunlight strikes the silicon with enough energy, it can knock an electron loose from its atom. This freed electron now has the potential to move through the material, creating an electric current. But simply freeing electrons is not enough. Without guidance, they would move randomly and no useful electricity would be produced. This is where clever engineering comes into play. Solar cells contain two different layers of silicon that have been specially treated through a process called doping. One layer contains extra electrons and is called the N-type layer. The other layer has fewer electrons and is called the P-type layer. When these two layers meet, they create an electric field at their boundary. This electric field acts like a one-way street, pushing freed electrons toward one side of the cell while directing positively charged holes toward the opposite side. As sunlight continuously strikes the cell, millions upon millions of electrons are released and guided in the same direction by the electric field. Thin metal contacts placed on the surface of the solar cell collect these moving electrons. When an external circuit is connected, such as wires leading to a battery or an appliance, the electrons flow through the circuit before returning to the solar cell. This continuous movement of electrons is what we call electric current. The electricity produced by solar panels is direct current, commonly known as DC electricity. In direct current, electrons flow in only one direction. However, most homes and businesses use alternating current or AC electricity, where the direction of current changes many times each second. To make solar power compatible with household electrical systems, an electronic device called an inverter converts DC electricity into AC electricity. This inverter is a critical part of every solar energy system because it ensures the electricity generated by the panels can safely power everyday appliances. A single solar cell produces only a small amount of electricity, usually around half a volt, that is not nearly enough to power a home. To solve this problem, manufacturers connect many solar cells together into a panel. Multiple panels can then be connected into larger arrays, capable of generating significant amounts of electricity. A residential rooftop system may contain dozens of panels, while massive solar farms can contain hundreds of thousands of panels spread across vast areas of land. The efficiency of a solar panel depends on how much sunlight it can convert into usable electricity. Early solar panels converted only a small percentage of incoming sunlight into electrical energy. Modern commercial panels typically achieve efficiencies between 20 and 25%, while advanced laboratory designs have exceeded 40% under specialized conditions. Although these numbers may seem low, the sun provides such an enormous amount of energy that even capturing a fraction of it can supply substantial amounts of electricity. Several factors affect how well solar panels perform. Sunlight intensity is perhaps the most obvious. Bright, direct sunlight produces far more electricity than cloudy conditions. However, solar panels do not stop working when clouds appear. They can still generate electricity from diffuse sunlight, although at reduced output. Temperature also plays an important role. Surprisingly, solar panels actually perform slightly better in cooler temperatures. While they require sunlight to generate electricity, excessive heat reduces their efficiency, which is why panels in cool but sunny climates often perform exceptionally well. The angle at which sunlight strikes the panel also matters. Panels generate maximum power when sunlight hits them directly rather than at a steep angle. For this reason, rooftop installations are usually tilted to match the local latitude, maximizing annual energy production. Some large solar farms even use tracking systems that slowly rotate throughout the day, following the sun across the sky. Although these tracking systems increase installation costs, they can significantly boost energy production. Another important component of solar energy systems is energy storage. Since solar panels only generate electricity during daylight hours, many systems include batteries that store excess electricity produced during sunny periods. This stored energy can then be used at night or during cloudy weather. Advances in battery technology have made solar energy more reliable than ever, allowing homes and businesses to reduce dependence on the electrical grid. If a solar system is connected to the public electricity network, any excess electricity generated during the day can often be sent back into the grid. In many regions, utility companies provide credits for this exported electricity through programs known as net metering. Later, when the solar panels are producing less electricity than needed, such as after sunset, the home can draw electricity back from the grid. This arrangement effectively allows the electrical grid to function as a giant shared battery. One common misconception is that manufacturing solar panels consumes more energy than they will ever produce. In reality, modern solar panels typically generate enough electricity to recover the energy used in their production within just 1 to 4 years, depending on location and manufacturing methods. Since many panels continue operating efficiently for 25 to 30 years, or even longer, they produce far more energy over their lifetime than was required to make them. Durability is another impressive feature of solar panels. Because they have no moving parts, there is very little mechanical wear. They are designed to withstand rain, snow, hail, strong winds, and decades of exposure to sunlight. Regular maintenance usually involves little more than occasional cleaning to remove dust, leaves, or bird droppings that may reduce the amount of sunlight reaching the cells. Scientists continue developing new generations of solar technology. Researchers are exploring materials called perovskites that may offer higher efficiencies at lower production costs. Flexible solar cells can be integrated into clothing, windows, vehicles, and portable electronics. Transparent solar coatings may someday turn ordinary windows into electricity-generating surfaces without blocking the view. These innovations could dramatically expand the places where solar power can be used. The significance of solar energy extends beyond individual homes. Large-scale solar farms now generate electricity for millions of people, helping reduce greenhouse gas emissions and slowing climate change. Remote communities without access to traditional power grids can install solar systems to provide reliable electricity for lighting, refrigeration, education, communication, and healthcare. Even satellites and space stations rely almost entirely on solar panels, demonstrating their remarkable reliability in some of the harshest environments imaginable. The beauty of solar technology lies in its simplicity. There are no engines burning fuel, no noisy turbines spinning, and no smoke rising into the atmosphere. Instead, sunlight quietly strikes silicon. Photons release electrons. Electric fields guide them into motion, and that invisible stream of electrons powers our modern lives. Every sunrise delivers an immense supply of clean energy freely to our planet, and solar panels provide one of humanity's most elegant methods of capturing that gift. As technology continues to improve and costs continue to fall, solar energy is becoming an increasingly important part of the global transition toward cleaner, more sustainable power, proving that one of the greatest energy sources we have has been shining above us all along.